Moment area method. Introduction. The idea of moment area theorem or moment area method was developed by Otto Moore and later started formally by Charles E. Green in 1873. It is just an alternative method for solving deflection problems. In this method, we will establish a procedure that utilizes the area of the moment diagrams, actually the M over EI diagrams, to evaluate the slope or deflection at selected points along the axis of a beam or frame. And what is moment area method? This is one of the easiest methods for finding deflection and slope of a beam with the help of area of bending moment of the beam, which is loaded with some load or any moment at any point or on whole span. When the superposition technique of indeterminate beam accelerated according to following reasons, restrained and continuous beams differ from the simply supported beams mainly by the presence of redundant moment at the supports, then the moment area method can be used. It is convenient to use this method with great advantage in the following type of problems. First, it is a cantilever beam or cantilever beams slope at the fixed end is 0. Number 2, simply supported beams carry asymmetrical loading, slope at mid span is 0. And beams fixed at both ends, slope at each end is 0. And for the deflection of beams, assumptions for slope and displacement by moment area method are as follows. First, beam is initially straight. It is elastically deformed by the load such that the slope and deflection of the elastic curve are very small, and deformations are caused by bending. So these are the assumptions for slope and displacement using moment area method. For the theorems of our moment area method, first, the change in slope between the tangents drawn to the elastic curve at any 2 points A and B, so this is point A and point B, is equal to the product of 1 over EI multiplied by the area of the moment diagram between these 2 points. So we have the load and the moment diagram. And from point A to point B, based on the moment diagram, the solid color blue is the area based on the point A up to point B. CG is the centroid of this area, and from centroid up to distance A, which is designated as X sub A, and from centroid up to point B along X distance or X axis and designate as X sub B. And the dotted line is the slope or the deflection, and this is the tangent line at A and another tangent line at B. And the angle formed from A to B, it is tangent theta or theta A sub B, and the proportion from at point B, we have the tangent line at B and tangent line at A. And the angle theta, which is theta at A to B, it is equal to 1 over EI and multiplied by the area from A to B based on the moment diagram. And for theorem 2, the deviation of any point B relative to the tangent drawn to the elastic curve at any other point A in a direction perpendicular to the original position of the beam is equal to the product of 1 over EI multiplied by the moment of an area about B of that part of the moment diagram between points A and B. And the formula for deviation from B to A, it is equal to 1 over EI times area of AB multiplied by the distance from the centroid up to point B, which is along x-axis, that's x sub B. And the deviation from A to B, it is equal to 1 over EI multiplied by the area of AB, and we multiplied by the distance from the centroid up to point A along x-axis, or x sub A. So these are the formulas to be used if you're using theorem 2 to find the deviation. And for the rules of sine, the tangent line at A and intersect at tangent line at B, from A to B, we form theta AB, and the sign is positive, which is counterclockwise. When A up to B, tangent of B, we can form an angle which is theta AB, and the direction in this example or in this diagram, sign is negative, or it is clockwise direction. So rules of sine in this case, for counterclockwise, the value for theta AB is positive, and for angle theta AB based on clockwise direction from A to B, and the sign is negative. For the deviation from B to A based on the tangent line and vertical up to point B, the sign for the deviation from B to A is positive, and also for A to B, wherein the slope is counterclockwise or clockwise direction, the sign is negative, or the deviation of at any point is positive if the point lies above the tangent, and negative if the point is below the tangent. So this will be your basis. If the line from A up to B lies above the tangent, then it is positive, and negative if the point is below the tangent. So the deviation of any point is positive if the point lies above the tangent, and negative if the point is below the tangent. And measured from left tangent, if theta is counterclockwise, the change of slope is positive, and for negative, if theta is clockwise direction. Process to calculate deviation. First, apply Theorem 1 to determine the angle between two tangents, and Theorem 2 to determine the vertical deviation between these tangents. And we realize that Theorem 2 in general will not yield the displacement of a point on the elastic curve. When applied properly, it will only give the vertical distance or deviation of a tangent at a point A on the elastic curve from the tangent at B. And then, after applying either Theorem 1 or Theorem 2, the algebraic sign of the answer can be verified from the angle or deviation as indicated on the elastic curve. So these are the process to find the value for deviation.